able to cover the spectrum of possibilities with the type of densest objects that gravity may harbor. But I would venture to say that many of the talks in this conference may actually utilize the latest messenger that we have for nature, namely gravitational waves, as probe of the characteristics of these objects. This talk is based on several works, and they're not limited to this list here, but additional papers will be noted in the slides. But of course, it has been informed by many more works and conversations with not only members of the LIGO Scientific Collaboration and the LIGO India project, but also scientists beyond those collaborations. So the broad talk line is the following. Yes, we aim to test general relativity by probing its solutions. And in this case, we'll be using solutions that have a strong gravity around them. And so two of the extreme solutions known to us are black holes and neutron stars, which have been probed in multiple ways and not just by gravitational waves. The properties that I'm going to leverage for studying them, mostly in this talk, are tidal heating, mainly for black holes, and tidal deformability for neutron stars. I think other speakers in this meeting will utilize other properties as well of these objects to be able to distinguish them, but also perhaps to probe the nature of gravity. Now, when I am, as I go through my slides, I think I'll wear mostly an observer's hat, but as Shorjo alluded to, maybe the first time I met him was in 1996 at the Strings meeting in Toshali Sands near Puri, where actually we learned, unfortunately, that Abdus Salam had passed away. So it has been more than a couple of decades. But at that time, I was a hardcore theorist, much less so now. So, but time to time, I'll try to use the observer's hat to walk you through how we can squeeze the theorists or the theory space, right? By which I mean that, yes, thanks to these observations, theorists will have to sit up in their armchairs, and the error bars in our observations are still leaving them with some playing field. But we are trying to squeeze those error bars. Nevertheless, it will be nice to see if there are alternatives to general relativity that survive. And if so, how much operating space they have, and how do they challenge the theorists to come up with alternatives to GR. Of course, there are fundamental reasons why we think GR may not be the ultimate theory of gravity, and one such reason comes from the possible quantization of gravity. I think some of the other speakers will talk more about it. If there are questions for me later in the talk, I may touch upon this myself. So that's basically what I'm trying to say in the fourth bullet here. So how much measurement room do we leave with these observations? So far, there's a lot of room, but maybe I can make some projections on with future detectors, how that room may shrink. So talking about observations, it's amazing, isn't it, how things have advanced over the last 5-6 years, where this set of gravitational wave detections by LIGO and Virgo was released as their first catalog. So GWTC 1. This was, if I recall correctly, somewhere perhaps at the end of the second observation run. In the first observation run, we had confirmed detections for 3 binary black hole collisions. That was followed by several more binary black hole observations in the second observation run. But perhaps extremely interestingly, we also observed a binary neutron star merger, and not just by LIGO and Virgo detectors, but also accompanied by a slew of observations by electromagnetic observatories across the spectrum. And they taught us a lot about neutron stars, their equation of state, but also, for example, how they enrich the universe with heavy metals, including gold and platinum, but they also told us about other interesting aspects about these high energy phenomena, such as in astrophysics, such as short duration gamma ray bursts. They also confirmed that kilonovae, which had been reported prior to 170817, this binary neutron star merger, were actually associated with these mergers. So it has been a whirlwind tour, I think, for all of us. And these charts are perhaps a staple diet for most of you by now, but I've been advised by some of the organizers that in some cases it is perhaps useful to flesh things out, especially because we're also looking at absorbing new junior colleagues to this pursuit of understanding gravity. So what we show here in the vertical axis is just the masses of the components and also the merged products, so the post-merger objects in solar mass units. So going from something like one solar mass to of the order of 80 solar mass in this first catalog. The horizontal axis doesn't mean anything. It's just there to space things out for easy viewing. Lower masses are populated by neutron stars, and all of these yellows are essentially neutron stars detected in binary systems within our galaxy. So in binary neutron star systems, of course, if it comes to neutron stars anywhere in the galaxy, there are hundreds of thousands of them. Not all of which are detected, but something like 1,000 to 2,000 of them have been detected as pulsars. We all know that. But binary neutron star systems are interesting because we know that at the later stages of their lives, when they're just minutes or hours away from merger, they will show up in ground-based gravitational wave detectors. And we have seen some of them already. The ones that we have seen in LIGO Virgo are highlighted in this with this orange balls. Of course, when they merge, they produce heavier objects. Signals from these post-merger objects have not been seen, but we are targeting them as well because they will have complementary information about the nature of these densest objects. I mean, whether they collapse immediately to a black hole or not has to be confirmed. Theoretically, we expect that for these kind of masses, the collapse will not be immediate. Chances are that the equation of state of this nucleonic matter is stiff enough, meaning there is enough pressure for the density of these objects, so that they will withstand gravitational collapse for maybe tens of milliseconds. But as they lose angular momentum and get more compact, eventually gravity will give in, and the final object is very likely going to be a black hole, following a hypernuclear or supranuclear phase. But during that phase, as the collapse is setting in, maybe there are phase transitions that happen. Maybe kaon condensates or other kind of quark matter show up in the core, and will they have any imprint in the gravitational waves they emit? Theorists have not been stopped in exploring these options, and so which is another reason why experimenters are tightening their belts to see if we can improve the sensitivity of these detectors at the frequencies that we expect these signals from, which is essentially towards the high end of our ground-based interferometric bands. And I'll talk a little bit about that as well. So one of these collisions is a confirmed binary neutron star. This is the 170817, confirmed also because the electromagnetic output was consistent with two neutron stars colliding to form a more massive object. In the second case, 190425, one of them is very likely a neutron star with the mass of something like, as it shows here, 50% more than the mass of Sun. But the other object is almost twice as massive, and so it may or may not be a neutron star. We can't be completely sure, even though neutron stars, I mean, right now, the most massive neutron star that has been observed has a mass of something like 2.14 times the mass of the Sun. And So, but the gravitational wave signal did not have enough information at enough sensitivity to tell us whether both components were actually neutron star in this second object observed in 2019. Also because, this was a farther object, something like at 160 megaparsecs, where a parsec is 3.26 light years, compared to this 170817 collision, which was much closer at 40 megaparsecs. So, of course, somewhat more distant than the Virgo cluster, which is at something like 15 megaparsec or so, but not as distant as the Coma cluster at 90 megaparsec. So, somewhat beyond local group, but still pretty close to have a large signal-to-noise ratio. The purple ones here are black holes observed in our galaxy through X-rays, primarily being emitted by matter falling in, accreted from a companion. The blues are the LIGO-Virgo black holes, and we are showing not only the parent black holes, so the lighter ones that merge, but also the daughter black hole that is formed, and usually more massive. And of course, there is a bit of a mass loss that we anticipate because of energy loss through gravitational waves. But the mass and spin of the final object is primarily inferred by using numerical relativity. So for these final objects, again, it is challenging to observe the signal from this final object because that signal will be essentially in the form of a ring down, something that Vishu pioneered in the late 60s, early 70s. And many other researchers developed further. So there are recent claims of possible detection of a post-merger signal, in this case from actually the prototypical binary black hole merger, namely 150914. I think we'll have to wait for the jury to finally confirm that or otherwise. But this is also telling us that, yes, to be able to aspire to see these post-merger signals, which are exponentially damped sinusoid, we need to build better detectors and maybe also wait for nature to cooperate, help us out by offering a golden black hole, which is relatively close and not, black hole binary, not as far as some of these objects, which is like 400 megaparsecs or beyond. But if you wait somewhat longer, so by the end, by the middle of the third observation run, notice how the population had grown from, of the order of 10 in the first catalog to something like 50 in the second catalog. And you can anticipate that these pictures will actually become useless very soon because it will be so crowded, right? So people are already thinking about how to channel this information in a uncluttered way in the future. But we are not complaining. More observations are extremely interesting because look at what I just said. Yes, there is the in-spiral signal, which lasts for several cycles, and we are able to gradually build the signal-to-noise ratio and see the cumulative effect above the detector noise floor. But then if we are aspiring to see weaker effects, okay, because of maybe predictions from alternatives to GR, or even confirmed GR effects such as quasi-normal modes for the post-merger signal, then one way out may be to combine information from all of these objects. Now, combining them is also challenging because there are variations across these observations, right? The masses are varying. Presumably, their spins are also varying, even though, interestingly, most of these objects appear to have very little spins. There are important exceptions, though. So, and it's good that there are exceptions, which means that not all of them have the same, formation history. They could have formed, especially now talking about binary black holes, maybe because of, field binaries of stars, eventually, having their cores collapse at the end of their lives, and then form these binary black holes. Of course, not all of these binary stars will result in binary black holes. Some of these binaries may get disrupted towards the end of their lives. But there are other formation scenarios where binaries can form through captures, right, aided by multi-body dynamics. Now, and in the latter scenario, you can have interesting orbits, not just nearly circular orbits, but maybe more eccentric ones. And yes, with more observations, you expect that the absolute number of oddball events will also climb, and that is fantastic. Yes, so far we have actually seen some of these oddball events where we just see a few cycles, presumably from such captures. And they may have some eccentricity. Strong eccentricities may also hint at such capture history for binary formation. But then, if there are captures, for example, in globular cluster, then there are other accompanying facts that have to be tested for. For example, we expect in such capture events that the masses of the components of the binary should be very similar. And that is because in globular cluster, you expect that over their billions of years of history, some kind of thermalization would have happened. And so mass segregation would have happened. Exceptions are there, but it makes our job much more interesting. So out of these 50, again, we also learned that, yes, nature has a preference for forming binary black holes, more than the binary neutron stars. Before 150914, we could not have said that conclusively. But this is what we are finding. And it's not just because of the fact that we can see these objects deeper, but yes, being able to see them deeper because their signals are louder is a primary reason. So 46 of these were, let me think about this. No, maybe even 48 of these were binary black holes. One of them was a binary neutron star. A second one was either a binary neutron star or a neutron star black hole. By the third catalog, so this came out recently, end of last year, I think December 2021. And yes, you see how cluttered these pictures are becoming. In the past, we could show the parent black holes coming in with different arrows, but of course, those are just schematics, right? Like here, merging to form a daughter. But now we really had to collapse all of these into single arrows. So two parent black holes forming a daughter black hole. So we have 90 of these. Now, don't ask me why we come out with catalogs when we have multiples of 10 observations, right? But that is how historically things have been. Out of these 90, 86 are binary black holes. We still have that one gold-plated binary neutron star, 170817, 190425, possibly a binary neutron star, neutron star black hole. But we also have two neutron star black hole events in this mix. Okay, so things are interesting. Are we able to capitalize on these pairs with neutron star in them to understand neutron star physics more? Unfortunately not. And that is because except for 170817, the other objects have been pretty far away. So it's good we are observing more of them, which tells us that yes, maybe future will show us some of these events with neutron stars in them that are close enough so that the matter physics encoded in their waveforms can be deciphered from the signals. So yes, I mean, I think for the younger generations, people who are doing their PhD and postdoc, things are extremely exciting. And it's not just because of gravitational waves. Other speakers, I hope, will talk more about how multi-messenger astronomy is being kickstarted with gravitational waves to understand these objects better. In this talk, I'll focus mainly on how do we tell whether there are horizons in binaries. There are other talks, and one such talk I'll advertise it is one of my former students' talk, Shag Datta. He will talk way more about this, but I'll perhaps give you some flavor of how can we tell whether these are black holes or some other objects, right? The working assumption in this talk will be that these are black holes or neutron stars in general relativity. So the onus is on others to prove otherwise, right? So the alternatives, of course, there's a multitude of them. For one thing, these may not be black holes or neutron stars, even though they're still compact objects in general relativity. So what might they be? Could they be boson stars, gravistars? I'm not exploring them in toto. But what I will tell you is a test that we and others around the world have developed of checking for horizons in these binaries. And boson stars and gravistars, for example, the way they have been proposed, I mean, they won't have horizons. So in that sense, they could perhaps be distinguishable. So in that sense, our tests will be less model specific. We'll make less assumptions about alternatives, but we will be driven by what we know from black holes in GR. For example, the energy that they capture from their orbits in binaries in the form of tidal heating. So that is the smoking gun for us to be able to probe the presence of horizons in binaries. I already mentioned in GR, you could have non-black holes, non-neutron stars, exotic compact objects. But of course, exotic compact objects have been proposed even beyond GR. And perhaps there will be other talks we'll talk about them. But then if you include non-GR possibilities, then there is again a whole plethora of them. I'm not going to channel predictions from them, except perhaps one case where there are some predictions from brain world, some flavor of brain world models for how the post-merger ringing of black holes will be much more extended and not exponentially damped, which could be a telltale way to check whether indeed we are talking about massive objects coalescing in brain world models or general relativity. And yes, quantum gravity also predicts, for example, maybe the energy flux that is observed through the horizon of these black holes will be in discrete steps and will not be continuous. Such proposals have also been made, but these are the reasons why, so the job of theorists is to also inform experimenters. And so this is how we are telling experimenters that, yes, do whatever you can to improve your sensitivity where we expect these post-merger signals to be, so that we can test these hypotheses. A possible holy grail in these tests will be, to check whether we can look for horizons in binaries in non-model specific ways. As I said, maybe we come close, but we don't do a fully model agnostic way of testing things. Now, yeah, this talk is not going to talk about many other interesting possibilities, like propagation effects, massive graviton theories. 17017 did constrain some of these theories, and even the LIGO-Virgo collaboration has used them to bound the mass of the graviton. Again, there are different reasons for why the gravitational waves arrived at us separated from the electromagnetic waves, such as from the short duration gamma ray burst. For example, because of the gamma ray burst model itself, right? So within GR, there are good reasons why there could be a second or so of delay between the arrival of these two signals. But as a theorist, if you want to use all of that difference budget to allow you to play with alternative models, you can do so. And massive graviton models were one such. So we have used certain models there using an IUCAA-like potential to say that, yes, the graviton mass cannot be any more than something like 10 to the negative 23 electron volts. So these are useful because some of these constraints have shaved off some operating space for alternative solutions. And then polarization tests are also important. They are becoming more viable with more detectors participating. So that is another reason why it is not too late for more detectors to contribute to this network of ground-based interferometers. Of course, the primary reason is to localize them in the sky better, which was the primary scientific case for building a LIGO-like detector in India, which, by the way, has already completed the construction of its first site building. Other studies are based on pre-project money. For example, the seismicity of the site, the weather conditions, and prototypical vacuum chambers, etc., are actually being built in the nodal institutes participating in LIGO India. So these are all exciting times. And we are just waiting for the full approval. I mean, the in-principle approval was granted in 2016. within a week or so after the announcement of the first black hole merger in February that year. So, but polarization test triggered this spiel from me, because with multiple detectors, it becomes more feasible to measure not only the two polarizations of GR more precisely, but also test for the presence of additional polarizations beyond those two. Tidal heating, that is, the drainage of orbital energy. Okay, I see a chat message. I may choose to collapse multiple questions. Can we use polarization tests for black holes? Is it possible for a black hole to emit a scalar wave? So other speakers are perhaps better positioned to answer this. The simple answer is in GR, no, because whether they're black holes or neutron stars, we expect only two polarizations, right? The plus or the cross, or their circular, polarization combinations. There can be additional polarizations in alternative theories of gravity. And binary black holes could, yes, also emit them. So scalar waves in Brans-Dicke, I don't think is possible. For example, you have basically the Schwarzschild solution there. But I've not surveyed other possible, whether there's a breathing mode possible. Maybe Luke and others can comment on that, but let's come back to that. Feel free to raise this question later. Now, but how do we test for whether there is absorption through the horizon? We can even, with ground-based detectors at the moment, what we have in our hands is, of course, access to stellar mass black holes, and maybe even somewhat more massive objects that could have formed in other ways, like with masses of the order of 100 solar mass. Whether those are stellar mass black holes formed through stellar collapse of what were initially main sequence stars, that scenario is getting more and more tested now. But ground-based detectors can actually observe binaries of black holes with masses as high as even a few thousand times the mass of sun. And in all of these objects, we can check for horizon absorption of radiation coming essentially from the orbits. But that has, and so this is something we are in the process of testing. Even though I will tell you right away that these tests are difficult. It may be easier to find imprint of tidal heating in supermassive black holes, which would be a staple for LISA-like experiments in space, such as through extreme mass ratio in spirals, where tidal heating does leave a very clear imprint on a dephasing of the orbit. But talking about orbits, yeah, this is our bread and butter. The very well advertised, first signal from 15 to 914 showed, of course, we only saw the last few cycles before merger, but all of these binaries will have waveforms that are like this or somewhat distorted versions of it. The black hole waveform is shown in the black trace here. Neutron stars, which can lose energy also because of their tidal deformation, right? They can get to the largest order quadrupolarly deformed, and how much deformed they are, again, tells us about their equation of state, and that can create this dephasing, as shown, for example, in this blue trace. And this is important because it tells us how it allows us to measure the tidal deformability parameter. But if there are other objects, there the waveforms could be even different. Even for binary black holes, if there is a strong eccentricity, there will be an interesting phase modulation. Which we use to measure the degree of eccentricity of those orbits, right? If there is spin modulation, then that will have another kind of effect. But not just that, even the post-merger signal also has interesting imprints. For binary black holes, you'll see this black trace where you have the damped sinusoid for the end. But for a post-merger signal from binary neutron star, you can have an extended oscillation, which is somewhat damped. from this the hypermassive neutron star. But then, if you have a scalar cloud of, say, ultralight bosons around an otherwise binary black hole, even in GR, right, that can also create some deviations from this vacuum solutions of GR. So that's one thing to note. The other, the complementary aspect is that, where do you observe these signals? Of course, I showed you time domain signals, but I will later show a frequency domain version of it. But in the frequency domain, this in spiral for non-spinning, circular binaries has, so the characteristic amplitude falls off like the frequency, the instantaneous, gravitational wave frequency raised to the -7/6. Okay, so in a log plot, it is a constant, slope, power law. And that is something you should keep in mind when you parse these noise curves, strain versus frequency, where the sensitive band is from around 10 hertz to a few kilohertz. So with the real detectors have noise curves, which like in advanced LIGO, we know it is different, and we have not yet reached this, design sensitivity. But it will look like the advanced LIGO curve shown in black here. And I'm going to show some results for that curve. The green is the next version proposed, A+. So, right now we are, we ended O3 around March 2020, just before COVID started. And then since then, we have been upgrading the detectors as well we can with these constraints from the pandemic. At the end of this year, we plan to start the 4th observation run, where we hope to be very close to this design advanced LIGO curve. And then we'll take a break again after about a year of observation for further improvements. The R&D for which is already in progress now. And with that R&D in the 5th observation run, maybe a few years from now, we hope to have this green sensitivity with A+ configuration. And then, of course, that has not kept the experimenters for thinking ahead. Other possible future versions would be a few times more sensitive detector called the Voyager configuration, or order of magnitude more sensitive detectors such as the Einstein telescope in magenta here, or the Cosmic Explorer in the red here. I mean, these are, yes, very ambitious. They will have technologies, several of them beyond the first three, such as cryogenic detectors, underground layouts, and so on, longer arms perhaps. So the R&D for some of this is already underway. I'm going to use some of these for some of the projection plots I show for how much we are able to squeeze that space for theorists, right? So now, what are the main conductors for horizons in GR? Of course, neutron stars. But neutron stars can only do so much, in the sense that, yes, if you make observations where the binary components have masses between 1 to 3 times the mass of Sun, then there is a chance that these are neutron stars, right? Otherwise, especially above 4 or 5 times the mass of Sun, it's unlikely they're neutron stars. So then either we are talking about black holes, or boson stars, or graviton stars, or the echoes, broadly exotic compact objects, right? In GR or without, or outside of GR. But even this neutron star scenario is interesting, because, in other words, there is something for purchase here. If you have light mass objects, if you have detected them, and some of which we have, like the 190425, right? If we expect this the matter signal, right, or matter distortions to be present in these signals. In other words, if the binary is close enough, and we expect tidal deformability owing to the nuclear matter of these putative neutron stars to leave an imprint that is detectable by us in those gravitational signals. Or, for example, if they had an electromagnetic counterpart that makes it very clear that it has to be a double neutron star, for example. Okay, but on the other hand, if we don't see any imprint of tidal deformability, right, then it will force us to again go back to the drawing board and reanalyze. I mean, what could these objects be? I mean, that's when the exciting prospect is that, these could be black holes, low mass black holes, never before observed, right? The lowest, the least massive black hole that has been confirmed observation is of the order of 5 or maybe times the mass of sun, or in that ballpark, right? So at least beyond gravitational waves. But if you see something like 1 to 3 times the mass of sun or lower, but you don't see any but with neutron stars for tidal deformability, this is the range where we'll see them. But here too, beyond about 1.7, 1.8 times the mass of sun, observing tidal deformability becomes very difficult, because this matter signature dies very fast with increasing mass. So we have a small range to play, but even in this range, if we expect tidal deformability but we don't see it, then it could be an indirect way of telling us that, okay, maybe there are light mass black holes involved, could be primordial. So we have not come across that scenario yet, but we are looking. At higher masses, like 4 or 5 times the mass of sun or beyond, are there alternatives to black holes? Even in GR, there are. I mentioned scalar clouds briefly. I'll show some signatures of them later, again, through modeling. But there can be signal distortion also because of gravitational lensing. Gravitational lensing, even with electromagnetic sources, for the type of distances we are able to see with LIGO Virgo, we don't expect the probability of signals to be lensed to be very high. But again, with increasing number of observations, the absolute number will become finite soon. So yes, so the exciting and with scalar clouds, if you do see a distortion of an otherwise binary black hole merger that cannot be explained in any other way in GR, then a scalar cloud influencing their overall mass and their orbital dynamics would be interesting to seek out. So now tidal heating, let me talk a little bit more about it before I show some expected signatures. So here, this is a diagram which may not appeal to everybody, but for theorists who deal with Penrose diagrams, for example, especially of the compactified version, then you know that, yes, this is my event horizon. This is the time like future infinity. This is Sky plus, and this is the source of some perturbation. I mean, this is generically representing, for example, any perturbation, but I'm focusing on gravitational perturbations. This could be essentially the impact of an orbiting companion, and such a companion will perturb the space-time around our black hole here. Okay, this could be a tiny compact object orbiting around a supermassive black hole, for example, in an extreme mass ratio in spiral, fodder for ELISA-like missions. So what we know from theory is that the waves that are created by such orbital dynamics, they will of course have ingoing fluxes described nicely through that psi zero Newman-Penrose scalar, right? Which can also be thought about the projection of shear, the shear on the horizon here, right? And then there is psi4 or the news, which whose derivatives give you the gravitational waves that escape to Sky plus, right? And these will be correlated. So what falls in will actually have an imprint on the gravitational waves far out. But if this is a spinning black hole, then remember that we can not only energy can fall into the black hole, but the Argo region can also be a source of energy flux coming out of the quote-unquote hole, and that will also leave an imprint on gravitational waves. So those are the kind of imprints that we look for in these binary waves. And by the way, I may not always spell out the names of these authors, but here, for example, some of my colleagues, especially Vaishak Prasad, who is a current PhD student in IUCAA and a senior researcher on Shugupta, they contributed to these studies. and also my colleague Badri Krishnan and Eric Schnetter. So, but tidal heating, it has been shown again by multiple authors such as these, that it's going to be much more pronounced by several orders of magnitude for black holes compared to other known compact objects such as neutron stars, something like 10 to the 14 in these units compared to 10 to the 4. So for all practical purposes, this energy that I'm talking about, going into a black hole, by the way, Charles, in this case, they analyzed it in the black hole paradigm framework, the black hole membrane paradigm, I'm sorry. There, so for all practical purposes, you can actually take tidal heating to be 0 for, say, neutron stars, as opposed to black holes. And, but essentially, the flux that gets out of the system, it has a part which comes even when there is no tidal heating, and such as for binary neutron stars. But then there is a piece because of tidal heating, and if both of these components in the binary are black holes, then both of these fluxes will contribute to a signature in psi4, and therefore the gravitational waves that go out to Sky plus. Here H, so I is the number of objects contributing. People who are examining soft graviton theorems and their implications for say supernova collapse, they will have multiple objects getting scattered and contributing to gravitational waves. So they will have I spanning a large number. But for us and for this talk, I will be at most 2. So there are 2 horizons possible in this case, H1 and H2 for the 2 binary components. If there are no horizons, then the values of H1 and H2 are 0. So this is how we bring in these tidal fluxes. And this work, for example, initially in my group at least was contributed by Shai Datta, but it grew beyond that collaboration with other members in the group. But as I keep saying, many other people have contributed to this, and I'm sorry I'm not able to do a full survey of the field. But some of these papers I encourage you to read, which are more complete in that survey. Because of those fluxes through the horizon, there are effects of TH means tidal heating. And those effects are captured at various post-Newtonian orders. So at the 5th post-Newtonian order, fifth power of V, which is really 2.5 post-Newtonian order, because those orders are given in powers of V squared over C squared. There is one combination of the horizon parameters, that H1 and H2, which combine with the spins to give rise to an effective parameter in the gravitational wave phase, which we call H effective 5 because of this 2.5 PN appearance. Right, but then there is another H1, H2 piece, the horizon piece that appears at a higher order, the 4 PN order, which we call H effective 8, alongside some residues from H effective 5. But essentially, there are 2 naturally occurring parameters, H effective 5 and H effective 8, that appear in the gravitational wave phase, which encapsulate information about the more direct horizon parameters, H1 and H2, and they're binary, whether the horizon is present or absent, 1 or 0. So, and there are details of these, coefficients of phases involving spin orbit coupling, etc., coming through the orbital angular momentum and the individual spins of the components. Again, more details I encourage you to read in these papers. But if you're interested in what H effective 5 and H effective look like, then this is how they look like. Don't go, I mean, I don't want to inundate you with details. The primary message is that the coefficients here depend on the component masses, small m1, small m2. Small m here, or big M, is the total mass of the binary, and also the spin parameters, chi1, chi2. I mean, these are the dimensional spin parameters with a maximum value of 1. And the smallest value is 0, but they can have, signs. So,
Sukanta,
yeah.
So we have 15 minutes to go. So if
I'll try to finish in about 5 to 7 minutes max. Thanks for the alert. Okay. So in the rest of the slides, I tell about how viable or not it will be to measure these parameters. If you do simulations without doing data analysis yet, then also the story is rich, and we show that this H effective 5 on the left and H effective 8 on the right, they vary with the effective spin, which is an interesting combination of the spins of the components that is measurable very well through the gravitational waves, just like the chirp mass is, right, as opposed to the component masses M1 and M2. And we show here that, yeah, if the spins, well, first of all, if the objects don't have horizons, for example, if they're neutron stars, boson stars, then both of these horizon parameters are 0. So if you are able to measure them to be 0, then your binary does not have horizons. Again, here the working assumption is we are talking in GR. But the problem is that even when the spins, chi1, chi2, of the two objects vanish, one of these parameters, at the higher, at the more leading order, H effective 5 goes to 0. And the weaker parameter, H effective 8, luckily is non-zero, but it's more difficult to measure. And you can see that, very close to chi effective of 0 here. And for the colors here show the different mass ratio, M2, the secondary mass over M1, the primary mass. So nevertheless, if the spins are large, then the H effective 5, H effective 8 values can be large, anywhere between like -4 to 4 for H effective 5, and of the order of -40 to 50 for H effective 8. So these are the astrophysical ranges in which we can check whether we are able to detect them. I mean, if you see these finite values of these parameters, then basically you're detecting spinning black holes in GR. I mean, that is what where my money will be. And by the way, are these observationally sound parameters? These are covariance plots. Now this is where I'm bringing data analysis, where this work has been explored by one of my PhD students, Shamana Mukherjee, and multiple set of my former students and collaborators, like Shrishti Tiwari, new postdoc. But here they're showing that if you look at the principal axis in this parameter space of horizon parameters, then like an Einstein telescope, in that noise curve that I showed, these two parameters are pretty much along the principal axis. I mean, these are match values at like 99% of match, going down to 70% of match in blue, and all of these are very well aligned. So these are the covariance is less, so the statistical independence of these two parameters is almost vanishing. So they give you independent information about the horizons of the two objects. If you are able to measure them well, then you can invert the equations I showed you to be able to measure whether the horizons are indeed zeros or ones, meaning if the horizon is absent or present respectively. Similarly, in the Einstein telescope also, they are statistically independent. In advanced LIGO and Virgo, they show some tilt, so some covariance, but it's still pretty small if you look at the axis carefully. And but we retain them for a study for all of these interferometers, essentially to facilitate comparison of the error bars across them. And you can come back and look at the details of these talks from the recordings. Because of lack of time, I'm going to flash them, but we do also Bayesian parameter estimates to show how well they can be measured or not. In LIGO Virgo, for sources at 200 megaparsec, the error bars are actually quite large, like 100% or more. But if you have a golden binary within 100 megaparsec, very unlikely, then we have some fighting chance to have error bars less than 100%, something like 40% or so. But Einstein telescope and Cosmic Explorer with total mass of 50, but at other masses also these error bars are not very different. There we are actually able to measure these horizon parameters much more precisely. Yeah, these are zoomed in plots for LIGO Virgo and Einstein telescope. Again, look at this in H effective 5, H effective 8 parameters. The injected values are shown very similar to the best measured value, and the error bars are shown in this plus minus numbers. And then Cosmic Explorer. So more trend plots are also given that you can visit later in this work. That you can access from the archive also. We show how these errors change as a function of total mass for both of these parameters. And then, okay, many more, basically greater range of the parameters for total mass and luminosity distance as well as spin. And the trends are expected. Of course, the errors will increase as you increase the distance primarily because of the SNR decrease. But then there are confounding aspects which I wanted to touch upon before ending for the null test of a black hole in GR. So I mentioned gravitational lensing and scalar clouds. So let me show some effects. This is another work by Anuj Mishra, Anuprita More, and Ashish Meena, and Jasjit Bagla, where the black is the trace of a binary black hole waveform unlensed, okay, without lensing. But if there is micro lensing, then depending on the parameters of what the surface density of the lens is, what the impact parameters are, what the amplification factors are, you can have distortions of both kinds. I mean, you can have a say a less magnified micro lensed image in, for example, in red, or a magnified image such as in blue. And this is the frequency trace I was talking about, where here the power law of the amplitude is something like f to the -7/6. Right, so some distortions can happen even because of lensing. So if you see a distortion, please don't jump to that. Oh, maybe GR is wrong. Okay, there are other very sane arguments for why distortions can be present. Scalar clouds, it's not clear whether how viable this is, but that has not prevented numerical relativists to actually mimic the effect of these clouds, such as by modeling them as in a complex scalar field influencing otherwise vacuum gravity. Now, the mass of the scalar field here, again, as I said, these could be ultralight bosons, a cloud of ultralight bosons, is ms. But this mu c is expressed in terms of the Compton wavelength of those bosons relative to the ADM mass of the full spacetime, which is dominated by the masses of the two black holes orbiting. Right. So mu tilde is basically our key to get a handle on the boson mass here. It turns out that the waveform of the merger and the ring down of these binary black holes with scalar clouds on them can be modeled very well with sine Gaussian waveforms. Okay, so these are sinusoidal waveforms with a Gaussian amplitude envelope. And this shows as you vary the mass of the boson and also the scalar field, cloud strength phi naught, then this is the effect you have. This has been explored in this work by other student of mine, Sunil Chaudhary, and other colleagues. So we are showing how by modeling this, the effect of the scalar field through this kind of a Gaussian, you can tell whether you can measure the mass or not. So I'll jump to, for example, this tells us how well you can measure the frequency, because the frequency itself, that's the first quantity you measure in these post-merger signals. And but you also measure the damping time, right? So by using those parameters, and these are very well measured for systems that's like 450 megaparsec, like for our typical binary black holes in LIGO. So this tells us that you can use those measurements. So if this is 165 hertz, then by looking at the distorted waveform, you can put exclusion diagrams. You can rule out certain or rule in certain ranges of masses for the scalar boson and the strength of the scalar cloud phi naught. Okay, so this is the range of masses and partial phi naught range that can be constrained if you measure the frequency to be 165 hertz in this example. Let me, okay, the neutron star also can, of course, mimic, let's say, binary black hole signals, especially at low masses. So between 1 and 2 solar mass, primarily because of the tidal deformability, this shows that we can discriminate binary black hole signals in red with large base factors compared to binary neutron star signals in black. Here, both cases, we are trying to detect and measure them with binary black hole waveforms, right? But for high masses where tidal deformability decreases, you notice that the two curves are pretty much on top of each other. And I think Sayak Datta will talk more about these things in his talk later in this conference. This is about tidal deformability, which I think Tanya, Hindra, and others may talk about. So I'm going to, brain world predictions also tell you how, for example, the mass radius, TOV curves will change, and how the measured posterior of the mass radius from 1708 17 will change but these changes actually move differently as you increase the brane world parameter here. And so that can also tell us or give us some bounds on this brane world parameter. And similarly, the quasi-normal modes can be different in brane worlds. So let me end with this, that various parts of the compact binary signals can be used to test general relativity. Of course, we talked mostly about how to use tidal heating in blind black holes, but some bit about neutron stars. Now, if you have multiple observations, while I didn't talk about it directly, but you can combine those signals, especially for common parameters, such as an equational state parameter or a brane world parameter, to constrain them, which can be useful for theorists. By combining electromagnetic observations, also you can learn, for example, about the equational state of neutron stars. And this is how they were helpful, because if the kilonova is bright enough, that means that the equational state cannot be too soft. Otherwise, not much matter would get tidally ejected. There are additional detectors that can help in measuring polarization, which I also touched upon initially. So I think the future of this field is extremely promising. We already detected nearly 100 sources, and there I've not counted some of the sources that other observers have claimed to have detected, who are beyond the LIGO-Virgo collaborations. But I think those also have to be seriously studied. So I think the future remains promising. On that note, let me end, and I hope I have some questions, or I can take some questions. Thanks.
Thanks, Sukanta, for a nice talk. And before taking up further questions, there was a question already posted in the chat box. Let me read it out. It is by Kanti Jotania. Is it possible to distinguish 2.5 post-Newtonian heating with radiation reaction of gravitational wave emission?
Yeah, so it is possible. I've not shown those slides. I'm hoping Shaya can show them. But a simple answer is yes. If the object is loud enough, and I think this is more possible with the extreme mass ratio in spiral like sources. And yeah, time will tell whether Cosmic Explorer as a ground-based detector or Einstein telescope will get built sooner, or will LISA get launched sooner. But maybe they will coexist in the same time frame, in which case one can also do other kinds of synergies, by the way. But the simple answer is yes, people have shown that they can be distinguished.
Okay. Okay, so Ashmita has a question. Ashmita, you may unmute and ask if you wish.
Yeah, hello, sir. Am I audible?
Yes.
Yes.
Yeah, so my question is that in LIGO data, is there any even tiny deviation in the speed of graviton than that of photon, which may motivate us to study the theories beyond GR?
Right. So, as I briefly mentioned earlier, the simple answer is no. And what we are doing is we are essentially timing the arrival of these signals, right? What we have not done is measure when the signals were emitted, right? If they were emitted at different times, then that could also mean that the arrival times will be different. But assuming that all of the difference in the arrival time is because of things like gravity having a mass, right? Under those extreme assumptions, we have put some bounds, and these still tell us that the graviton mass is extremely small. But if you want to take that as an allowance for you to explore alternative theories, then yes, to that extent you can do so. But that's not the only kind of test. There are other tests that people have proposed. For example, through dispersion relations, right? That if graviton has a mass, then because the inspiral signal actually is a broadband signal,
yes, sir.
With a spread of frequencies, then the dispersion relation, if it is non-trivial, that means that the
radiation will depend on the mass.
Let me finish. For the benefit of other users, I don't want our fields to overlap. But yeah, you can come in later. but precisely, so the late inspiral signal, for example, will appear at a different time than predicted by GR. So a change in the chirp signal also, in principle, can hide information about things like graviton mass. Essentially, an interesting dispersion relation. So the error bars allow us some space in that regard. But nothing is significant there for us to conclusively say, oh, you know what, we are able to establish that gravitons have a mass. So that has not happened yet. By the way, there are other tests that maybe Arun or others may talk about here. So for example, the post-Newtonian waveform is very well modeled, and it's extremely accurate at low frequencies. But we can tell, we can hypothesize that there are deviations from if there are deviations from post-Newtonian theory, they can be modeled through some allowances in these coefficients in the post-Newtonian part of the waveform. And the measurement of those coefficients have actually been presented even in the December 2021 paper for that third catalog. And there also we don't see any deviation that is significant to talk about. From GR predictions. Nevertheless, there are error bars, and question is, how much more we'll squeeze them with more observations.
Okay, thank you, sir.
Thanks.
Okay, Shayan has a question. Shayan, you may please unmute and ask.
Yeah, so my apologies to Shayan that I didn't talk about our wormhole example, but I hope that also gets talked about at some point. I mean, those are other kind of alternative objects that may exist, and in our paper we explored their signatures. There too, I think LISA-like missions will have a better shot at establishing them or ruling them out. But here the question is regular black holes, for example, barred in space-time, say, and usual black holes with singularities. Okay, both have horizons. Yeah, can one distinguish them from? Okay, so. My knowledge here is limited to some advising or some suggestions I was giving to another postdoc colleague of mine, Mandar Patil. Of course, he was looking at other kind of naked singularities, like the one by Newman and others. Now, the simple answer is that I think the spacetimes are different enough that one can devise tests to probe these differences, but I am not aware of any work that has shown, with projections, like, how much the differences in the waveform can squeeze the parameter space available. But from some of the studies that I've seen, I think in principle, they are distinguishable in some cases. But how viable it is in observations with future detectors, I have not studied.
Okay, good to see you. Thank you for a nice talk, Sukanta. Good to see you and hear you as well. Okay.
Okay, Shailesh
Thanks.
has risen hand. Shailesh, you may just unmute and ask.
Yeah, thanks. So I have a slightly different question. In the context of this tidal heating, are there any possibilities, or can this tidal heating effects show the signatures of asymptotic symmetries like super translations? Even if one considers the inspiral phase correction to the due to this tidal heating, I don't know if one needs to consider the cluster of binaries to have the signatures of asymptotic symmetries in the context of tidal heating. So, are there any possibilities in this direction?
Again, I have not looked at the problem myself, but I have been present in meetings where people like, Abhay, and in some cases, in other cases, Ashok Sen, I mean, they have been, Abhay Ashtekar, and they have been present. And if I understood their thoughts correctly on this, I think in principle, some aspects of them may show up in our waveforms. But like with the horizon parameters, H1 and H2 show up as combinations with masses and spins in the form of what I call H effective 5 and H effective 8.
Mm-hmm.
So whether these super translation, symmetry related parameters, if they are able, if the gravitational waveform allows us measurement of them individually or not, I doubt, but as combinations in some clusters, maybe.
Okay, I see.
Okay, so the last question, this will be the last question. Kanti has asked that when is now LISA likely to be launched? So do you have any idea about that?
The last I heard was a note from the European Space Agency, right, the parent organization, which, Dr. Elias Wagner confirms is 2034. I was going to give the same date, but maybe his date comes with is much more sanguine than mine, although we agree on the number.
Okay, thanks very much, Sukanta, for a wonderful talk.
Thank you.
So thank you for your time.